Ancient people saw them as messages from the gods, as supernatural winds that blew from the realm of spirits. Modern science has linked these polar light shows, called auroras, to vast waves of electrified gas hurled in our direction by the sun. Today, researchers from a whole new generation see this dynamic substance, plasma, as an energy source that may one day fuel humanity's expansion into space. What can we learn? And how far can we go? By tapping into the strange and elusive fourth state of matter. Since the dawn of rocketry, we've relied on the same basic technology to get us off the ground. Fill a cylinder with volatile chemicals, contact! Then ignite them in a controlled explosion. The force of the blast is what pushes the rocket up. Nowadays, chemical rockets are the only ones with enough thrust to overcome Earth's gravity and carry a payload into orbit. But they're not very efficient. The heavier the payload, the more fuel a rocket needs to lift it into space. But the more fuel a rocket carries, the more fuel it needs. For long-range missions, most spacecraft rely on their initial launch speed to essentially coast to their destination. Flight planners often design routes that give the craft a gravity assist by sending it around the moon or another planet. One small cadre of scientists believes it has a quicker and more efficient way to get around in space. Dr. Ben Longmire and his team from the University of Michigan have traveled to Fairbanks, Alaska, to play a small part in a much larger push to revolutionize space travel and exploration. The team plans to use helium balloons to send components of a new type of rocket engine to an altitude of over 30 kilometers, above 99% of Earth's atmosphere. The purpose is to test these components within the harsh environment of space. While astronauts train to live and work in zero gravity, or to move around in bulky spacesuits, these would-be space explorers are preparing to negotiate some of Earth's harshest environments. Once they launch their payload, they have to retrieve it wherever it comes down in Alaska's vast snowy wilderness. The idea they're pursuing is nothing short of revolutionary. It's a type of rocket that promises far greater gas mileage than other rockets and enough power to reach distant targets. It runs on the same fuel that nature uses, literally, to power the universe. To understand it, we go back to the early moments of time and space. Not long after its explosive beginnings, the universe was awash in vast stores of hydrogen gas. But even as the universe continued to expand, gravity began to draw clumps of matter into ever denser concentrations. The earliest stars took shape, immense balls of hydrogen gas, hundreds of times the mass of our sun. As they contracted inward, they heated up and ignited. Intense radiation now began to flow through the voids. That had the effect, all through the universe, of stripping electrons away from the primordial gas. The universe became filled not with solids, liquid, or gas, but with a fourth state of matter, plasma. On our planet, plasma occurs only in rare circumstances. In a hot flame, a bolt of lightning, or in a blown electrical transformer. Made up of negatively charged electrons and positively charged ions, plasma is in most cases electrically neutral, since the charges balance each other out. That led the physicist Irving Langmuir in the 1920s to compare it to the clear liquid plasma that carries blood cells through our bodies. The development of radio led to the discovery, high above the Earth, of a natural plasma ceiling, the ionosphere. It hovers above us, reflecting some radio frequencies and absorbing others. The discovery of immense radiation belts beyond our atmosphere opened the way to the study of plasma in space. Unlike most matter on Earth, plasma conducts electricity and responds to magnetic fields. These properties influence the formation of structures like galaxies and nebulae. They power high-velocity jets that roar out of newborn stars or black holes. Studies of one giant nearby ball of plasma show what a complex and volatile substance it can be. In the core of our sun, high heat and crushing pressures cause hydrogen atoms to crash together. That sets off a nuclear reaction in which hydrogen atoms fuse into heavier ones like helium and carbon, generating heat. This heat slowly rises to the surface of the sun in vast plumes of plasma. You can see evidence of this process, called convection, in a pattern of ever-evolving blobs known as granules. They are like the tops of thunderstorms. Even as energy builds within, the sun's gravity and density can stifle its escape. What carries it out are magnetic fields generated by the rising and sinking motion of hot plasma. They twist and wrap around, channeling energy to the surface. The fields can power immense loops of hot gas, about 60,000 degrees Celsius, then rise up from the solar surface and fall back. The sun can also erupt in giant waves of plasma that fly out from its surface. Called coronal mass ejections, they can reach up to 6 million miles per hour as they hurtle out across the solar system. When the solar wave strikes, it slams into Earth's own magnetic field. Because solar particles are charged, a portion follows the orientation of Earth's magnetic field lines. Finding an opening at the poles, they race down into the atmosphere. You know this is happening when you see the beautiful lights of the aurora borealis in the far north, or the aurora australis in the south. They appear when charged solar particles collide with oxygen molecules in the upper atmosphere, causing them to glow blue, red, and green depending on altitude. Flying through a zone called the thermosphere, some 350 kilometers above the Earth, astronauts in the International Space Station watch in awe as the aurora shimmers, framed by the glow of stars and cities at night. It's the explosive properties of plasma that have motivated the collaboration between NASA, Ben's team, and a company that he's affiliated with, the Ad Astra Rocket Company of Houston, Texas.
So many cameras.
Because plasma does not occur naturally on Earth, the challenge is to create it, then harness it in a rocket engine. In the lab, the teams do this by injecting argon gas into a chamber. They bombard it with radio waves, which strip electrons from the gas and turn it into a plasma. The soup of electrons and ions accelerates as it moves through a magnetic field generated by superconducting magnets. Then it's hit with a second blast of radio waves that heats it up to 1,000,000 degrees Celsius. This hot plasma blasts out the back and propels the craft.
Okay, that's our ultimate goal.
As part of their design process, Ben and his team are testing some of the specialized components of their rocket in the harsh environment of space.
So we should just do.
A simple frame will carry an array of novel sensors. One holds a colony of bacteria.
The idea is that the bacteria itself can detect radiation. So it mutates in a certain way or in a very known way that when you send it into an environment with a lot of cosmic rays and a lot of perhaps X-rays from the aurora itself, it mutates. And so we'll detect sort of the level of radiation that it's exposed to by looking at these mutations after we recover the bacteria from flying it to the edge of space in these balloon capsules.
Another is a series of tiny GoPro cameras converted to record the intensity of infrared and ultraviolet light normally hidden to the human eye. Argon gas is used to insulate instruments against the cold, with chemical packets added for warmth. The frame is stabilized with tiny gyroscopes and outfitted with GPS devices for tracking. The idea of using plasma to power rockets is not a new one. The Polish physicist Stanislaw Ulam is said to have been inspired by atom bomb tests in the 1940s. He speculated that waves of plasma from small nuclear detonations could propel a spacecraft to extreme speeds. In the 1950s, that idea animated dreams of exploring the solar system in spacecraft like this 360-ton Mars-bound vehicle. The idea gained funding in the Orion project, with the idea of driving a spacecraft with nuclear pulses and landing on Mars in only a month. Concerns about radioactive exhaust helped doom the project. Plasma rockets, energized by nuclear reactions, were revived in the Daedalus and Nerva projects of the 1960s. And again at the beginning of this century, as part of a journey to Jupiter's moon Europa. Rising costs killed that mission. Ben's efforts rely on simpler, far less expensive methods. Their payload has flown all night, up to an altitude of over 100,000 feet.
Where we believe the target is.
Then, in the low air pressure, the balloon burst, and the payload parachuted to the ground.
Off trail from here all the way up to here.
We've got GPS units, all the coordinates plugged in. We're about 26 miles from here as the crow flies. We're about 35 miles by trail, last 5 miles being really off trail, so we're gonna have to break some new trail.
They know exactly where it is. But that doesn't mean retrieving it will be easy. It takes nearly all day to travel well-packed trails to a point about 7 miles from their prize.
Payload is marked.
Oh, so we are heading down south. We are on this road.
The rest of the way will take them through forests and over hills.
That way is north, payload's west, we're kind of going.
A brave attempt through the deep snow. The team gets to within 2 miles. The next day, a long hike and snowshoes finally gets them to the payload. To this team, the effort is worth it, for plasma rockets could finally have their day. A real-world test being designed by the private company Ad Astra could take place as early as 2016. It fits a real-world need. Flying at an altitude of 350 kilometers, the International Space Station whips around the Earth every 1.5 hours. To stay aloft, it must maintain a speed of 28,000 kilometers per hour. But its solar panels and crew modules smack into so many tiny molecules in the upper atmosphere that it gradually slows down and loses altitude. To stay aloft, the station uses up around 4,000 kilograms of fuel per year. That fuel must be flown up from Earth, which in turn reduces the amount of food, water, people, and equipment that a resupply mission can deliver. The idea is to use a plasma rocket to help boost the station to a higher altitude, powered by electricity generated by solar panels aboard the station. Ben is also working on lower power rockets for much smaller spacecraft. The idea is to mount them on tiny desktop-sized craft called CubeSats. Based on this miniature model, he imagines sending small solar-powered rockets to remote locations in the solar system to collect scientific data, prospect for minerals, or even look for evidence of life. From there, the idea is to one day scale up the technology to power a human mission to Mars. After weeks spent accelerating in Earth orbit, the rocket would make a break for Mars. Cutting flight time from a year to several months would lower costs and crew hazards. Ben's ultimate goal is to help boost a whole new approach to space travel that's now emerging. May 2012 marked a major milestone in the rise of free enterprise in space. The SpaceX company successfully docked an unmanned space capsule with the International Space Station. It followed that up 6 months later with the first commercial resupply mission.
And launch of the SpaceX Falcon 9 rocket as NASA turns to the private sector to resupply the International Space Station.
That's just the beginning. NASA is looking to companies to supply orbital launch services and to be long-term partners in future manned missions beyond the moon. Hoping to make big bucks, companies are developing orbital habitats and space planes, laying the groundwork for missions geared to mining, exploration, and even tourism. To Ben, this new race to space will go to the swift and the innovative. Today, because of weather and winds, he and his team have chosen to launch their payload from the spectacular Ruth Glacier in Denali National Park. Amid the rugged terrain, this immense river of ice sweeps down into a perfect natural runway. With dusk approaching, balloon and payload are ready. The balloon drifts up through the dense polar air. With night falling, it rises up to the edge of space. Meanwhile, overhead, a solar storm is raging. Aboard the International Space Station, astronaut Don Pettit is making observations to complement what Ben's team finds. He passes over the Arctic several times during the balloon's flight. The auroras he photographs are an indicator of the amount of solar particles that will pummel Ben's rocket components. This is a time of high solar activity, approaching the peak of an 11-year cycle. This university-based experiment operates on the remote edge of modern science, dominated by large international projects such as the Hubble Space Telescope, the International Space Station, or the Large Hadron Collider. And yet, working small, Ben's team believes they are onto something big. Their goal is not only to open new avenues of space exploration, but to actually seize the initiative. It's a romantic idea of individuals challenging the odds and striking out to new frontiers. With technologies that are getting smaller and more powerful, who will hold back this new breed of explorer?